Today's video I would like to introduce a very nice problem of Turkish Mathematical Olympiad edition 2007-2008. Here is the following setup. Find all primes p such that we have this condition 7 to the p minus 1 minus number 1 is divided by p is a perfect square. Okay, I have been working on this one and came up with a nice proof, which is a nice and quicker method. Okay, we say in this fraction is a perfect square, which means this one is going to be written on this form. So we'll have 7 to the p minus 1 is divided by p equals x squared. Okay. So first table, as you know, the prime number can be even prime or odd prime. Okay. So let's check maybe if p is an even prime. If p equals 2 as an even prime, I'm going to insert this value of prime into this fraction to see what's given us. So we'll have 7 minus 1 over 2 equals x squared equivalent x squared equals 3. But this one is not a perfect square, which means it's impossible to be an even prime, which means p must be an odd prime. If p is an odd prime, let's set p equals 2m plus number 1, where is a m is a some natural number. Okay, and so why I'm writing this one on this form? Because this is standard form for the odd integers, but it's not every prime is an odd integer. Next thing up, replace p minus 1 with its value, so we'll have 7 to the 2m minus 1 is going to cancel out. 1 equals 2m minus 1 equals p is multiplied by x squared, like this. Okay, since this one is a difference of two squares, now we are able to factor this one out by putting this one on the form of the product. So we'll have 7 to the m minus 1 factor 7 to the m plus number 1 equals p is multiplied by x squared, like this. Okay, so as we know, this term is an even, this one is also an even, which means the right hand side of this equation must be even as well. Since both terms are even, which means GCD of this one equals 2. Okay, I'm not going to solve this one as an equation, so I'm going to solve this one as a divisibility notions. Okay, we have two possibilities here. We have p can divide 7 to the m minus 1, or p can divide 7 to the m plus number 1. Okay, so we are going to prove one of the term must be eliminated. Okay, so by the way of contradiction, suppose p divides 7 to the m plus number 1. Okay, if p divides 7 to the m plus number 1, this is implies x squared must divide the other one, which is 7 to the m minus 1, like this. Okay, so according to the divisibility statement, this one it can be written on this form: 7 to the m plus number 1 is congruent to 0 mod p. Okay, in the other word, 7 to the m is congruent to minus 1 mod p. Okay, let's call this one as a statement number 1. Let's look for the other one. And also, since p divides 7 to the m plus number 1, this is implies also p not divides 7 to the m. Okay, because 7 to the m plus number 1 and 7 to the m are prime numbers. Okay, in the other word, 7 to the m not divide 7 to the m plus number 1. Okay, what is this one telling us? This one is verifying the Fermi-Taylor theorem. If you have p as a prime divides an integer, which means a to the p minus 1 is congruent to 1 mod p. So the same thing here, we are going to apply the Fermi-Taylor theorem on this. This one is telling us 7 to the m to the p minus 1 as an exponent is congruent to 1 mod p, like this. Okay, so by taking this exponent off, so equivalent 7 to the m is congruent to 1 mod p. Okay, here is a second statement, which is statement number 2. Okay, so we have the same number, 7 to the m is congruent to minus 1, at the same time is congruent to 1 mod p. Okay, so which means I will have 7 to the m is congruent to minus 1 is a congruent to 1 mod p, like this. Okay, so by taking this number 1 to the left, I get minus 2 is a congruent to 0 mod p. Okay, this one is telling us p divides 2. Okay, which is impossible, because based on the previous proof we have shown p not divides 2. Okay, so we have a contradiction now. So what we have contradicted? We have contradicted p not divide 7 to the plus number 1. Since p not divide 7 to the plus number 1, which means p must be divide 7 to the m minus 1. Okay, this one is telling us 7 divides 7 to the m minus 1, which means p divides 7 to the m minus 1. If p divides 7 to the m minus 1, this one implies x squared divides 7 to the m plus number 1. Okay, since this product is even, if you put them together, this whole evenness is going towards x squared, which means the whole evenness is going to the x squared, which means 4 divides x squared. Okay, if 4 divides x squared, which means x squared is a multiple of number 4. In the other word, equivalent x squared is a congruent to 0 mod 4. Okay, if x squared is a congruent to 0 mod 4, which means 4 divides 7 to the m plus number 1. Okay, so when it's telling us 4 divides 7 to the m plus number 1. Okay, that means 7 to the m plus number 1 is a multiple of 4. Okay, so in the other word, 7 to the m plus number 1 equals 4 is multiplied by c, where is c is a sum natural numbers. Okay, and also since we have proven p divides 7 to the m minus 1, okay, equivalent 7 to the m minus 1 is a congruent to 0 mod p. Okay, equivalent 7 to the m is a congruent to 1 mod p, like this. Okay, here is another statement. Here is an important statement here. Let's call it statement number 3. In addition, we know 7 is a congruent to 1 mod 3, because this difference 7 minus 1 is divisible by number 3. So by raising number 2 as a power on both sides, I will get 7 squared is a congruent to 1 mod 3, and by multiplying by number 7 on both sides, I will get 7 cubed is a congruent to 7. 7 is a 1 more 6, which is congruent to 1 mod 3. Okay, the same thing here. 7 to the 4 is a congruent to the 1 to the 4th is a congruent to 1 mod 3. This one is going all the way down to the 7 to the m is a congruent to 1 mod 3. Okay, here is another statement. Let's call it statement number 4. So by using this fact and this fact, we have 7 to the m is a congruent to 1 mod p. Also, we found 7 to the m is a congruent to 1 mod 3. This one is telling us p must equals to 3. By using this fact number 2 and number 3, because we know 7 to the m plus number 1 is a multiple of 4, as we have here, which means if I'm going to replace p with number 3 here, I will get 3 equals to m plus number 1. I will get m equals number 1, like this. If I have m equals 1, I will get 7 plus 1 is 8. 8, exactly 8 equals 4 is multiplied by 2. Okay, so which means 7 to the m plus number 1 is a multiple of 4. Okay, so that means the only value of p that we have as a prime, which verify in this equation. So we have determined p equals 3 as a prime. If I'm going to replace p with number 3, I will get 7 square, which is 49. 49 minus 1, which is 48. 48 divided by t is 16. 16 is the same as 4 square. Okay, so which means I have p equals 3 with x equals 4. Okay, this is the solution for this equation, the prime. So I have done with problem. If you are interested in watching this one, don't forget to support us with your like and subscribe. Thank you for watching. I will see you next video. Bye.